Run out of time. You ran it out of time. Too late to change it. it's looking like you ran out of time. It was out of 10 points. I think what I'll do is I'll just drop it out of 8. Because it looks like it's the last 2 questions weren't reached. So we'll do. All right, so that should be about done. All right. We're good. All right, so yeah, this is equation. It's going to be either z or t, and it could be written as x minus mu. Could be x bar minus a value x. All right, but more than likely it's going to be mu. But remember, it's always taking your standard error. That's what you're always dividing by. So, all right, so that was by hand. What we are going to do is we'll probably do, I'm going to get the t-test and the sign test up as like a quiz. And that's going to be done in R. So we'll get a data file posted. You'll download the data file. And then it won't be like, I might set it up as an RMD so that you can fill it out as an RMD file. But then the quiz will be asking for specific values. So it's asking for the test statistic or degrees of freedom or the p-value or the interpretation and so forth. So if you went through this and felt like you had an idea of what the hypotheses were, what your test statistics were, and so forth, it felt decent, with the exception of not making to the last 2 problems, you're feeling okay. If you weren't sure what hypotheses were, then go ahead and start filling out that sheet. So, close. Remember, we posted test summary. Open this up. Enable editor. So we have test summary statistics. All right, so we can just kind of fill this out as to how I would approach it, because I know our exam's coming up. Thanks, Anna. I would have been 1 week late on it. All right, so we're going to do our test. All right, we'll fill out like the z-test and the one sample t-test first. So z-test, all right, that's what we're working on. This handout was, again, posted on Blackboard. All right, test summary students. So I'm actually going to save this. You can go to my biostats folder, and then I might do like a new folder. We'll just do notes or something like that. However you want it. But I'm going to call these basically their name. So this will be our z-test. So number and type of variables. So here we have 0 qualitative variables, and we have 1 quantitative variable. And this quantitative variable, it's not really independent or dependent. All right, does not apply. So I'm just going to go ahead and, when I highlight it, I'm going to go ahead and use like one of these font up here and just strike it through, just so we know it's 1 quantitative variable. Our additional information for our z-test is that we're comparing a single variable to a known mean or something like that. Single variable could be 1 item, could be a mean of a sample. Our assumptions, we didn't really list a whole lot of assumptions for this because we're dealing with the sample, but normally our assumption with a z-test is that our variable is normally distributed. And that allows us to make that transformation. So when we take x minus mu, divide by the standard error, it approximates a normal distribution, which thus allows us to utilize our normal curve. So our null hypothesis then is our x or x bar is equal to our mu. And I could go in there and do like your X bar. And I could change that to symbol. So if we insert symbol, normally the symbol is it's going to be one of the ones that you've used previously. So I've used it before. And then this is, I'll just do X or X bar is not equal. I use my exclamation point for that. So our test statistic, NA, degrees of freedom, NA, right? Because we're not doing that. And then our function or code is 2 times P norm of X, whatever value we're looking at, and then we're specifying the mean and our standard deviation, which is the S over square root of N. And then lower dot tail, let's do lower dot tail equals T, because we're going to add a description to that. Right, so I think we have all of this in our handout, or in one of our R markdown files, but we're just kind of getting this filled out, so we have 1 sheet per test. So our description, right, for a 2-tailed test, we multiply by 2, like above. X is a numeric vector, or a numeric value, not a vector, just a single value. That's what we're testing against. Mean and SD refer to the population. That should actually be sigma. So I don't have sigma up here. I'm going to click on my more symbols. And then I'm just going to move down until I find the Greek letters. There it is. Sigma. There we go. Insert. Close. That's sigma over square root of N. Refer to the population. N is the sample size of X. And lower dot tail equals T when X is less than the mean. Lower dot tail equals F when X is greater than. Right. All right, and then you can have your example. So find a data set, and for this, we don't really even need a data set. Right? We can go back and look at some of our old examples. Let's open this up. Less likely to struggle. Navigation. Is that better? Should have spoke up. So we can find an example from our notes, or you can make up an example that follows it. And for the data set, I'd probably just give, like, we measured 5 items and the mean is some value. Is this mean equal to the population with a mean and standard deviation or something like that? So just kind of lay out the data set, lay out the what question could we ask with this problem, which for us, I think I would do. Question is our sample mean equal to the population, or is our sample representative of the population? That could be a question that we have. And then I would have the R code and paste it below. So let's do a data set. Let's say we have we measured 10 worms, and we'll say the average size is, we'll do 80 millimeters. Say 10 tapeworms, 80 millimeters. Pretty big tapeworm. Not unusual to find them in humans. Is our sample. Is the mean length equal to that of two? So Taenia, human tapeworm. Actually, I'll do solium because I'm not entirely positive on that spelling. So we've got mean is, I don't know what it is. Not 80 millimeters. We're going to change that to centimeters. We'll make it more realistic. What is our average? Oh my goodness. The average is reported as between 2 and 7 meters. So between 2 and 7, we'll say 4. That would be 400 centimeters. And we'll say sigma is 25. I don't know how realistic that is. So the question is, our sample representative of the population? R code. Let's go back to R. So I already have R Markdown open. I'm just going to create a new R script because we're going to do this two-tailed test. So we're going to do our P norm of 80, where our mean is 400. Standard deviation is 25 over the square root of our sample size, which is 10. Lower dot tail equals T. So I use the same format. So 80 is our sample mean that we're comparing. Our mean of 400, that's our Taenia saginata. Standard deviation, that's 25 over the square root of 10. So it's a standard error using our sigma. Since we use sigma, that approximates our Z. And we're using lower dot tail because this value here, this 80, is less than the 400. All right? And then when I run it, I get this, which makes me very concerned because it's so small. So what I'm going to do is I'm going to highlight these two lines in the console window. So these two lines, I'm going to copy it and paste it into my Word document. And I say it's a little concerning because you get 0. Anytime you get an output of 0, it's like, okay, did something happen? Did my numbers get transferred over or not? Who knows? But here we know, yeah, we're so far away from 400 that our p-value is going to be just like absolutely super small, super small. So I'm not too concerned. But then we have our write-up. So our mean length is not equal to that for Taenia solium. And then we do our z-test, and p is less than 0.001. And just to confirm that that's what it is, I can always go back. I can always go back to my R and change that 80 and get it closer. Make it, let's say, 300 or 350, just to demonstrate that yeah, it's going to work. It's going to give us a number. It's just we're so small that the chance we get 80 centimeters is pretty low. Now that doesn't mean that this isn't Taenia solium. It could be grown, all right, early on in infection. But if we're just basing it on the average length, we know that it's unlikely to be that. So yeah, just to demonstrate that that's what we had, I'll just go back and change this to 350. And when I run it, I do get a value. It's still pretty small. So 50 centimeters short, it's still a very small p-value. So that's pretty good. That's our z-test. So I would save that. And then I have this as my as a study guide, as a handout that I would probably keep. So outside of this class, if you need to do a test statistic and you say, okay, what do I have? You always start with, and we are going to have like a flow chart, but we always have how many variables, what type of variable do we have? These are the tests that are available to us. All right. So before lab, what you can do is do your t-test, one sample t-test, and you could do like your sign test and two sample t-tests. All right. Any questions? This is where we left off, right? Ask you to have this ready, do the test. Don't check the assumptions. Don't check the assumptions. We're going to assume that all the assumptions are met. So here's my write-up. Here's my write-up. So we've got raspberry.csv, and I loaded it in already. So this was the RMD file that we've been working on. Let's close that. So I have it right at the top, my read.csv file. I've got library car, I ran that. Don't need it because we're going to assume that all assumptions are met. So I'm just kind of laying out, does fertilizer affect raspberry production? That was our question. Our null hypothesis is that mean fruit of the Miracle-Gro is equal to the mean fruit of the organic fertilizer. Our alternate is that the means are not equal. We didn't specify if one was going to do better than the other. So then I said, at this point, we would normally check assumptions, but the problem said, assume that all assumptions are met. Or actually, the problem said, don't test the assumption. That's kind of code for assume that we're met. All assumptions are met. So if we assume that all assumptions are met, we're good to run the test, which is t.test, fruit is a function of fertilizer, data is raspberry, var.equal equals t, because we made the assumption that all assumptions, or we said all assumptions are met. And we wrote it as a formula, so our dependent variable is fruit, that's our measurement. As a function of fertilizer, that's our grouping variable. So then we get the output. We look at our p-value to make our conclusions. P-value is greater than 0.05. So we know we failed to reject our null hypothesis, which means then that our means are equal. Even though numerically they might be slightly different, statistically those means are equal. So our write-up, type of fertilizer does not affect raspberry production. I give my t-test, give my test statistic 1.54. I give the degrees of freedom. I use a subscript for that. And as I said, with your R markdown, if you put your subscript in like a curly braces, that'll work. So that way you'll just know that I'll read that as subscripts. And then p-value less than 0.13. Hopefully you had no problem doing that. So at least for the notes and stuff for the practice, definitely this is a good way to kind of go through and just kind of keep everything in order. Once you're out of the class and you're doing, let's say, an honors project, probably don't have to give all these details. You're just running your stats. Ready? I need to leave this up. Any questions on why I made this conclusion?
Why didn't you put the T after that?
Because I put it as a subscript to our T. So yeah, you can do it either way. You can do your T equals 1.54. So we can do it, or I can do it like this. DF equals 98, comma. That will also work. But when you're writing it in like a scientific paper, usually it's a subscript just to save on space. But we did present everything that we needed. Conclusion, interpretation, test statistic, test, degrees of freedom, p-value, all 5. All right. So t-test versus ANOVA. They have the same number and type of variables. So both of them require one independent variable, that's our grouping variable. Both require one dependent variable. That has to be our measurement, so it's either a continuous or a discrete variable. Our assumptions are the same. Data are random and independent. Data are normally distributed within each group, and we have equal variances. The difference between the two is that t-test can only be run when we have 2 groups. ANOVA can be run if we have 2 or more groups. All right. The difference then, when we have this 2 groups versus 2 or more groups, comes down to the test statistic. So a t-test utilizes the t statistic, t observed is our test statistic. In ANOVA, it uses the f statistic from an f distribution. ANOVA, because we're using the f distribution, is more robust to violations of our normality assumption. So if we are slightly non-normal, ANOVA is going to do just fine, whereas t-test might not. All right? So if we meet all of our assumptions and we only have 2 groups, we'll get the same p-value for both. If we violate our assumptions, the normality assumption, ANOVA is going to be a little bit better. So what is this analysis of variance? Or what is ANOVA? ANOVA is the analysis of variance. And I don't want you to get this confused. We're not comparing variance, even though it says analysis of variance in the name. We're comparing the means. And we compare the means by comparing the variances. But it's not all the variances. We're comparing variances within groups to variances between the groups. I don't think I have an image in here. So let's go to the board and we'll explain what's going to go on.
If it's not analysis of variance, why do you think that?
Because you're going to see how we can utilize the variances to determine if means are different. All right, so our variances that we're going to utilize is variances within groups versus variance between the groups. And this kind of gives us what I've termed a signal and a noise, where the signal tells us the likelihood that our means are going to differ, and the noise is all of the random variation that kind of makes it harder to detect the difference. All right, so I'm going to start off with, we're going to put up 2 different graphs. We're actually just going to focus on two groups, 2 data. 3 groups in our data. I'm not going to put a y-axis on here. So we're just going to have some sort of dependent variable. All right. And what we're going to say is x bar of A is equal to x bar of B is equal to x bar of C. All right, that's going to be our first one. This one's going to be all means different. So our analysis of variance is testing if our means across the groups are the same. I have on the board. I have full size. Just want to make sure that. Yeah, we can see it. All right, so we've got all means. So all means is, we're going to start off with our A, our B, our C, A, B, and C. And what we're going to say is average of A looks right there, average of B is right there, average of C is right there. All right, and we're going to add some error. Now we've got A is there. We're going to make it even more. So B equals slightly higher over there, we're going to make B like really large up here. We're going to make C really small down here. So we still have our errors. The errors probably about the same. Probably about the same. But here's our two different data sets. One, all the means are the same. One, all the means are different. So why is it announced as a variance? We've got two things. We're going to calculate a variance within the groups. Then we're going to calculate variance between the groups. Right? So the variance within the groups is basically this. Our variance within all of our groups. And we tend to add them all up to get like an overall type of variation. Right? So this is all of our noise that we've had. And then what we're going to do is calculate our signal, which is the variation between the groups. Now, how do we do the variation between the groups? Well, what we're going to do is look at our grand mean. So I'm going to kind of eyeball it and get a grand mean, where it represents like the average of the averages. But it's more like the weighted average of the averages because it accounts for differences in sample sizes. But for us, we'll assume that they're equal. So what we can do then is look at each of these points to figure out what is our total amount of variation. And the way it does that is looks at each of our points, and however many data points we have, that's where we calculate the differences to that grand mean, and that we can calculate a variance. So in this one, we have very small deviations away from that grand mean, right? So that signal is actually going to be fairly small relative to the noise, which is our variance around each of our means. Here, though, if we look at how far each of these are from our grand mean, and we figure out how many sample sizes, the total sample size of the groups, now look at how many points we're getting. Look at how many of these are far away from that grand mean. So here, if we've got a signal, and we're relative to a noise, we're going to get something that is very small. Whereas here, our signal is going to be pretty large. So much so that when we look at the individual deviations of our group means to that grand mean, it's going to probably far exceed the individual variation that we see within these groups. So as this signal gets bigger and bigger and bigger and bigger, it makes it more and more likely that they're not equal. Now, where does the signal and stuff come into play? It's our sum of squares. So do you remember the sum of squares equations? Actually, let's just do our variance. Our variance equation is that x I minus the bar, x bar squared, sum them all up, divided by n minus 1, right? This is the sum of squares. That's what we use. And the question is, what's that value? That value can be the grand mean, which represents our signal, or it can represent our group means, which is our noise. Now you could say, well, hold on, we've got 3 different groups, so which group means do we use? Well, we're going to use all 3. You're going to calculate this for each of our groups and then add them up, and that's our total noise. Our grand mean is our signal. So if they're all equal, all of our means will be close to our grand mean. It's going to be very hard to reject our claim that these are different. But as we become farther and farther and farther away from our grand mean, our means are getting different. And thus we'll be able to detect it. Where does the variances come in? The sum of squares. That's what we're using. sum of squares just comes down to, are we doing the grand mean or are we doing our individual group means? Now we can do this by hand. It's really not too difficult. Especially if I set it up and I have it set up as a table where it's like this term is A and this term is B and this term is C, and then you have the equation, calculate your F statistic. Makes it actually fairly easy. But we're not going to do it. We're actually just going to use R to do this for us. All right. So that's where the variance comes into play. We're still comparing the means. That's our null hypothesis, is that the means are equal. But we're going to utilize these sums of squares to detect how likely it is that our means are actually different. All right, so the sum of squares is what we're going to use. As we add data points, our sum of squares should get bigger and bigger and bigger, which means what we'll do is divide by a degrees of freedom to kind of standardize, to scale it. And that gives us what's called a mean square, which sum of squares divided by the sample size is very similar to a mean, right? An average. Our relationships, sum of squares, we can add up our signal and the noise, and it comes up to a total sum of squares value, which is like all of our points, the sum of squares of all of our points. And then same thing with the degrees of freedom. I present this because this is the real benefit of ANOVA. So the approach to the analysis of variance is that we can start to partition all of the sources of the variation. So if we go into these group A, B, and C, and we say, okay, well in our groups A, B, and C, we also have genotype X and genotype Y in each of those. We can pull that information out so that we not only have sum of squares of treatment, but we also have sum of squares of the X and Y situation. And then we could say, well, what part of the total amount of variation that we see is attributed to the treatment, to our X and Y, and to the error? And if we add another variable, we can do the same thing. So there's a lot of benefit to using this approach. Our test statistic is this mean square. So our signal, this is really ultimately our signal to noise. Mean square of our treatment over the mean square of the error. We're going to see the output, some of the output. For us, we don't have to report any of this. We only need to report our F statistic. Now, what's important with this F statistic is that it's a continuous distribution, and it's defined by two values. A numerator degree of freedom, the degree of freedom that's used to calculate this treatment mean squared, and a denominator degrees of freedom, which is what calculates the error mean squared term. So we're going to need two of them, or actually, we're going to report both of those degrees of freedom. And then we're only going to get a single p-value because our F distribution is relating the signal to noise ratio. So if we look at an F distribution, it's going to look something like this. Right? If our signal and the noise are equal, what's the value of our F? So I should say this. If this mean squared treatment is equal to the mean square error, what's the value of F? 1. All right, and if mean squared treatment is the error, what happens if this gets smaller and smaller and smaller? We're going to be less than 1, right? Does that mean that they're like more equal? No, like you can't be more equal. I mean, you're equal. You're equal. So what's key for us is that we're really looking at this point down here. We're going to get a value that looks at that tail, because as our means start to become different, we're going to get a larger and larger value of F. So this is always going to be a one-tailed test. That's all we're going to run, because we're testing, are they equal or is one at least different? So what we're going to do in lab is we're going to start with this plant growth data set, and I'm going to show you how to kind of work through. We're starting with all of our assumptions, that all assumptions are equal. All right, and we're going to do our test, and we're going to learn about a post hoc test. And then we'll go back and check what happens if our assumptions are violated. All right, we'll pick this up in lab.